All right. It is about it's 7:42 a.m. The lecture will not start until about, I don't know, 7:55. I'll start the announcements and reminders, but I won't get into the new material until 8 o'clock. So if you're watching the video, your first word for attendance is going to be snow. Um, you can go ahead after that. Just a reminder, if you're watching the video, you're going to have to send, once the video is over, a list of the attendance words with a screenshot every time I say one of the attendance words. And then you're going to need to ask one question about the material covered in the video. But anyway, like I said, the first word for attendance is snow. So you should take a screenshot and I should see, what I see on the screen right now. And then you can skip ahead about 10 minutes into this video, um, because that's when the lecture will officially start. Thanks. Okay, it is 7:55. I'm going to go ahead and get started because today's announcements are really just reminders. There's no new information here. And I have a feeling no one's going to um, show up online for this lecture since it's not required. So anyway, I'll go ahead and get started. Let me really quickly go back to here to make sure I'm recording. Looks like my microphone is on, camera's off. I'm presenting, and looks like I'm recording. So let's see really quickly one more time to check. Yep. All right. So anyway, that being said, I'm going to go ahead and get started. So again, all this information is old. It's been available to you before, but this particular part about the extra credit, I've never really discussed it before. I've told you if I would explain it if you ever asked me to. And so I did receive an email yesterday from a student who was confused about their extra credit. So really quickly, I just want to explain how it works. When you earn extra credit, not only does it go towards the points you've earned, but it also goes towards the points possible. So as an example, let's say you did a pre-lab that had 10 questions, right? You didn't do any extra credit. You missed 3 questions, right? So you missed 3 out of 10, which means your score was 7 out of 10. And when you do the calculations, that's a 70% C. Now, let's say with the same pre-lab that has 10 questions, you also did 10 questions worth of extra credit, 10 points of extra credit. So not only is that added to your total points earned, right? So instead of 7, you now have 17, but it's also added towards the total points possible. So instead of 7 out of 10, right, we're adding 10 again to both sides. So 7 out of 20. Sorry, that looks so sloppy. So 17 out of 20 is an 85% B. Now, in this particular example, that made a pretty big difference, right? You went from a 70 to 85%. So when you only have a few questions, like in a pre-lab, it's going to make a larger difference. But, generally speaking, it's not going to make a lot of difference. And it's not meant to. It's not meant to be a game changer. And almost all the extra credit in this course, almost anyway, it's basically like you can do this if you want to, and it'll help you if you do it well, or you can just not do it. And that's basically how extra credit works. Anyway, moving forward, 7:57 right now. Again, you should have received an email and feedback on your lab because I posted a course announcement about this yesterday, but lab will not be in person today, right? Campus is not open until 10, so I can't expect, me to be there at 10, ready to go, you to be there at 10, ready to go, and then the person who puts our lab carts together, all the materials, like today would have been acids and bases, can't expect them to be ready to go. So I called it, and we're having an online virtual lab today. I'll be online if you need me using the same link that I'm on right now, but you're not required to join. So again, join me if you need help, and I would love to help you. I'd prefer to help you. That way I know you're learning the material, and also that you'll get do a good job, which actually makes grading easier for me. Anyway, like I mentioned when I first started about talking about lab being online today, like I said, you're going to be doing a different lab worksheet, right? It's a virtual version, and it's nearly the same as the one you've started. The pre-lab is exactly the same, so you don't need to worry about that. But again, to find that, you can go to the course announcements because I posted it there. Also for the feedback in lab 2, right? I went back and for everybody's lab 2 where you submit it, I left feedback. Even if you didn't submit anything, I left feedback that has the link to the new version of the lab. So let me know if you have any questions. As always, attendance is mandatory and the participation is graded. It's the same thing, but really quickly, I'll just mention it again. So when this is all over, you're going to send an email that has an attendance word or with a list of the attendance words with a screenshot of every time I said an attendance word and one question about the material covered in this lecture. Of course, if you're watching the video, you already heard me say that earlier because There was already one attendance word. So now let's do the second attendance word. And it's going to be, I'm going to circle it here. Your second attendance word is not a word at all. It's a set of numbers, and it is your course and section number. You are in 101-02. So there you go. And then finally, let's see here. Yeah, 8 o'clock. Before we get started really quick, I'll remind you exam one is scheduled for next Friday on February 6th. So make sure you bring your computer to class or whichever device you need. Bring it to class on Friday, because even though it's an online exam, we're going to be doing it in person. So you're going to need your devices, and you might need something to charge your device. So make sure you bring a cord if you need to. If you have any issues, like maybe you don't have a device that'll work or something like that, or you know that you can't make it on Friday or anything, make sure you email me beforehand and let me know. And likewise, if you need more time to take the exam, you need to let me know beforehand so we can make arrangements. Yeah, and I think that's it. And again, one more thing to remind you, exam one is going to cover chapters 1, 2, and 3. Obviously, we're in chapter 2 right now. Yeah, that's it. Oh yeah, and your study guides. So the quizzes on WVSU Online, those are your study guides. And like I mentioned at the beginning of the semester, you might get extra credit at the end of the semester for doing those quizzes. But I highly recommend it, because not only will you get exposed to some of the questions that will be on the exam, but you get familiar with how it works. Because as far as how WVSU Online works, the quiz is basically the same as the exam. The grades are different, but the way it's laid out is the same. So get familiar with it. Anyway, like I said, it's past 8. I'm going to go ahead and get started. No one is here, but that is fine. So this is where we left off. We left off talking about water, which is the second, like the middle portion of the chapter. And I've already explained all this. This on the slide right now. I mentioned that this is the one thing that you need to know from the slide, which is that your cells are about 70 to 95% water. So I think that was the second to last slide we talked about. So then we got to this. And what we're about to discuss, we're going to talk about these individually. So if you take notes, there's no need to write this down, because we're going to talk about the cohesive nature of water, its ability to moderate water temperature, the biological significance of the fact that ice floats, the versatility of water. We're going to talk about all of that. But I will say again, really quickly, the big picture here, before we move forward, the reason that water can do all these things, it's because of its polarity. Remember when we talked about polar molecules on the last video, those electrons are not shared equal. So one part of the water molecule has a slightly negative end, which is the oxygen, and the other part, which is the hydrogen, has a slightly positive end, right? So they attract each other. That's hydrogen bonds, right? So everything I'm about to show you is basically all due to the hydrogen bonds. So let's get started. All right, the first thing we're going to talk about is the cohesion of water. Again, like we've already mentioned a few times here, water molecules stick together due to their hydrogen bonding. And really quickly, I'll mention that this is called cohesion, right? When two things of the same type stick together, that's called cohesion, right? As opposed to adhesion, which is when you stick different things together. For example, if you had a sticky note and you stuck it against the wall because it has adhesive on the back of the sticky note, that would be called adhesion. Not that you need to know that, but it wouldn't hurt if you knew what cohesion meant. I might ask you the definition, but obviously I'm about to talk about it, so you're going to need to know what it means for that reason. So again, cohesion is when molecules of the same kind stick together. And this is also worth noting here. Water is more cohesive than most other liquids because of its polarity and its shape. So I invite you for extra credit to look up what are some other strong liquids, that have a strong cohesion. Which ones are close to water? Which ones perhaps are stronger than water? You can look that up for extra credit. Now, if you do that, don't send it on the attendance email. Send it on a separate email. And don't forget your sources. Anyway, so what's it matter that water is cohesive? What does that matter for life? So let me give you a few examples. And of course, as always, after I give you these few examples, feel free to look up some other examples. I'm going to give you what I think two examples of why the cohesion of water is important. And then after that, once we're done with the lecture, you can look up to see if there's other reasons why it's important. But anyway, first one we're talking about is the fact that trees depend on the cohesion of water to be able to transfer their water from the roots to the leaves. And that's pretty important when you think about it. So if you think about a huge redwood tree, hundreds of feet tall, how does the water get all the way down here from the roots in the ground all the way up to the leaves, right? Yeah, so the leaves, for example, get rained on, right? We know they get water on them from rain, for example, but they don't get any water from that, right? The only water they get is coming from their roots. And that's a big deal, right? How does it get that high up there? It's not like they have little water pumps inside of them. So let's talk about really quickly how they work. First of all, we can look here at this zoomed in picture, this microscope picture of a tree, and we can see that these, we have these little tubules, right, where the water flows, almost like a pipe, like a water pipe, basically. So imagine those are going way up top, and imagine a leaf at the very, very top of the tree. I'm going to try to draw a leaf. It's probably going to look horrible. I'm a horrible drawer anyway, especially when yep, especially when I'm using a mouse. Anyway, let's say that's a leaf. And what happens, and you don't need to know this much detail, but really quickly, there's something called transevaporation, which is when water leaves, the water molecule is going to leave the cell, right? It's going to evaporate into the atmosphere. So what happens is when let's assume this is what we're zoomed in on over here, right? When the water molecule leaves the cell, it is still hydrogen bonded to this water molecule. So it pulls it with it, which pulls this one with it, pulls this one with it, right? So that's how that works. And again, this is why the cohesion of water is important for trees, and it's how it works. And you can see again how it's due to the hydrogen bonds. The next thing we'll talk about is surface tension. I might ask you what surface tension is. So if I do, just in case, I'll give you the definition. Is the measure of difficulty in stretching or breaking the surface of a liquid. As a matter of fact, surface tension will be the next word for attendance. And let me give you a second to take your screenshot. All right. So anyway, yeah, it's the measure of difficulty in stretching or breaking the surface of the liquid. And as again, like I mentioned when we first started, this is all due to the hydrogen bonds, right? It's the hydrogen bonds are responsible for the surface tension. And this picture is a great example of it. You can see this spider walking on water, basically. And I want to point out really quickly that this spider really is on top of the water, which is different than floating. So, for example, if you had a boat, once again, a horrible drawing, I'm sure. There we go. Anyway, if that's a boat, that's kind of what a boat looks like, right? There's a part above the water, but there's also a part below the water, right? Boats are floating. Boats are displacing water, which is what floating is. These are on top of the water. They haven't even broken the surface of the water. Here's another picture to demonstrate that. So the water level is about right here in this picture with this Olympic swimmer. Actually, I guess this might be a little bit lower. But anyway, this person is above the surface of the water. But at this exact moment, when this photographer got this picture off, even though they're above the surface of the water, they haven't broken the surface of the water, so because of that surface tension. And here's just another good picture of surface tension. I like it because it's got our mascot, and I also think it kind of looks cool. But anyway, that's surface tension. So before we move on to the next one, I'll remind you again, suggest to you, if you want for extra credit, you can look up, what are some of the other ways that surface tension is important. Or if we back it up even more, remember surface tension was basically a subcategory of the cohesion of water. So again, you can look up more examples of why the cohesion of water and excuse me, Surface tension is important. But that out of the way, and let's talk about the second reason, the second property of water, right? Which is how water moderates temperature. This is a big one. It's pretty important. Um, First of all, before we talk about how water moderates temperature, the first thing I need you to do is define what temperature means. And this is important. Not only will you get tested on it, but you're going to need to understand this concept later in the semester quite a few times. So, what is temperature? When I say, oh, let me turn the temperature up in the house, right? What does that mean when I say temperature? Well, the definition is temperature is the measure of the motion, which is kinetic energy, and I'll explain that in a different chapter what kinetic energy is. Basically, it's the movement of motion. But anyway, temperature is the measure of the motion of molecules. Meaning, going back to my example, when I say I'm going to turn the temperature up in the house, what that means is I'm going to increase the motion of the molecules of the air molecules, right? So that's what temperature is. That out of the way, I can tell you that water has a stronger resistance to temperature change than most other substances. And again, before I go on and explain this, I'll again invite you to do an extra credit where you look up, okay, water has stronger resistance than most other temperatures or substances, but what are some other substances that are close to water or even better? Not that you need to know it, but you can look it up for extra credit. Anyway, let's talk about why that happens. Why is it that water resists temperature change? And then after we talk about why or how it does that, then we'll talk about why that's important. And I really wish we were in person, so I could kind of demonstrate this to you with like physically with my body. But anyway, when water is heated, right? Again, we're talking about temperature, right? So the temperature is increasing. We are increasing the motion of these water molecules. So try to picture, and I really wish I had a picture up, but remember we had these molecules drawn earlier, right? I'll try to draw a water molecule. Just try to imagine a bunch of them. I'm only going to draw one or two, excuse me. There we go. Now remember, there's a bunch of them. Hopefully in your mind's eye, you can picture the previous slide that had a bunch of water molecules hydrogen bonded to each other. But anyway, so remember, temperature is the measure of the motion of these molecules. So as we heat them up, and I wish I could animate this, these water molecules are going to be moving around more and more and more. But they're still bonded to each other, right? They still have that hydrogen bond. So they can't move around too much, right? Since they can't move around too much, that means the temperature is not going to change too much, right? Because the only way that we can get the temperature to change is if those molecules are moving. So what eventually happens once you give enough energy, you finally disrupt those hydrogen bonds, right? That's basically the boiling point of water is when you've disrupted those hydrogen bonds, right? They're no longer hydrogen bonded to each other and they're just moving freely. And then that's when things really get heated up. But again, because of those hydrogen bonds, because of them being together, it's harder to do that. And the example I like to give when I'm in person is just imagine a bunch of students standing up and holding hands, and I'm telling them move around a little bit. All right. And then move around a little bit more. And then move around a little bit more, right? And they're holding hands and they're just jostling around and twisting and as much as they can, but they're still holding hands. But eventually, they can only move so much while they're holding hands. But eventually, if they keep trying harder and harder, eventually they're gonna, they won't be able to hold on to each other's hands anymore, and they'll break those bonds, and then they can really move around, right? And that is again the high temperature. So anyway, because of this, water absorbs and stores a large amount of heat while only warming up a few degrees. And I don't know if you've ever seen anybody do this, but a great everyday hack that uses this principle is when people sometimes, they use a stove, and then when they're done using it, obviously there's a hot eye on the stove. A lot of times people put a tea kettle full of water on there. And the reason is that water will absorb the heat with very little change, right? Very little temperature change, Because if you're trying to keep your kitchen cool, that's what you want, right? You want something to absorb that heat. So now you know how that happens. And the question is, why does that matter for biology? Well, if it wasn't for that, Earth just wouldn't be what it is, right? It would probably be uninhabitable. The temperatures, well, even if it wasn't uninhabitable, the temperatures would probably be so extreme that life just couldn't, it either wouldn't be the same or wouldn't exist at all, right? So, in other words, what I'm saying is water helps the temperatures on Earth stay within the limits that permit life. So, again, without it, like when if you had a portion of the sun that was in, excuse me, portion of the Earth that was in the sun without water on Earth at all, that would just get really, really hot. And once the sun went away, it would get really, really cold. And a good example of that is there are some places on Earth like that. If you've ever been to a desert, generally speaking, well, depending on the type of desert, but anyway, generally speaking, a desert, most people associate them with being hot, and that is usually true. And they're usually very hot during the day because think about it. There's hardly any water in a desert. So the sun's beating down on the desert, and there's nothing to absorb that heat, right? Everything there is getting hot, right? Um, there's nothing, and again, there's no water to absorb the heat. All that stuff, everything in the desert, the plants and uh, the sand, the rocks, all that, it's getting heated very quickly because it's not water. So it changes temperatures quickly. It gets very hot. Doesn't do a good job of storing heat. Then the sun goes down. And again, there's no water. So again, all those other stuff, all those other things like rocks and the sand and things like that, it absorbed a little bit of heat, but not like water could. So once the sun goes down, it quickly gives up that heat. So then the desert usually gets pretty cold at night. And then compare and contrast that to like a beach town, like Myrtle Beach. And I know the temperature can fluctuate there too, but it's not quite as drastic. Because when you're next to the beach, you have the huge body of water, right? So the sun's beating down, and yeah, it's hot at the beach, but the water is absorbing a lot of that heat. Excuse me, when the sun comes up, it's beating down and it's getting hot. But again, the water is absorbing a lot of that heat. And then when the sun goes down, yeah, it gets cooler. But then the water is releasing that heat slowly. So there's not a huge temperature difference. And that's just one day. And the same thing can be said for, the course of a year, right? As we go from winter to spring to summer to fall, back to winter, right? Those large bodies of water slowly absorb heat and absorb, right, throughout the hot months, and then slowly release it throughout the cold months. And then finally, the last example I'll give of that would be ocean currents. And I'll show that on the next slide. Let's talk about, well, do I have that picture? Yeah. We'll talk about evaporative cooling here in a second. But anyway, yeah, picture this, right? So, West Virginia is right about here-ish, right? I don't know if you can see where I circled that. Iceland is about here. So that's a lot farther north, right? But look at the temperature. Look at this. And I looked this up, and this is what I found. And I don't remember my source, and I should have included it because that's what I always tell you to do. But anyway, West Virginia's average temperature in January is a high of 40 and a low of 23. Iceland's average temperature in in January is a high of 37 and a low of 27. So you can see like how similar that is to West Virginia. And we're so farther south than they are, right? So that is mostly because of water, right? So the water, here's the equator, this water right here is getting a lot of sun, right? Because it's at the equator. It hits South America, and it either splits. It either goes this way or this way. But anyway, we'll talk about this water, and it starts traveling north. And while it's still in the south, it's still gaining, it's still absorbing all that heat energy from the sun. But then as it gets farther north, obviously it has less sun and it does get colder, but that water is still maintaining a lot of that heat. It's giving up some of it slowly. So by the time it reaches Iceland, it still has a lot of that heat, right? So that's what keeps Iceland about the same as West Virginia as far as average temperatures are concerned. Another thing to point out too, and then we'll move forward from temperatures. Usually, the farther inland you are in a continent, the more drastic your temperature change. Again, due to the fact that um, water slowly absorbs heat energy and then slowly releases it, right? And let's look at this as an example, right? So if we're looking at West Virginia's average temperature, 23 to 40, that's nearly a 20-degree jump, right? So the low to the high is a nearly 20-degree jump. In Iceland, 27 to 37, that's only a 10-degree jump. So again, you can see West Virginia has a higher fluctuation from highs to lows than Iceland, because Iceland is an island surrounded by water. Anyway, that is it for how water moderates temperature. Of course, there's this picture of the desert, and I didn't explain what that means while it was on the picture. While it was on the screen. But I've already talked about how deserts get really hot during the day, and then generally get pretty cold at night. Anyway, let's move forward. Really quickly, like I said here, this one's really quick, and there's not much to mention about it. Water has evaporative cooling. In other words, sweat, right? So that's for a lot of animals. Sweat is the way we maintain the proper temperature in our bodies, right? Sometimes it gets too hot, so we sweat. That water gets hot from our body heat. It evaporates, and when it evaporates, it basically takes the heat with it, basically. So that's what helps us cool off. All right. So that's it for the first two. So again, big picture. Before I move forward, I want to remind you, we're talking about those properties of life that make it necessary for life. And this is the third of the fourth properties. And it is the biological significance of ice floating. So before we talk about why that's important, again, let's talk about how that happens. But before we do that, your first word for attendance is going to be ice. So again, write that down, take a screenshot, pause the video if you need to, because I'm moving forward. When water molecules get cold enough, those molecules move apart from each other, and that is what forms ice. Now, there's a test question about this. I'm trying to remember how it's worded. It basically says something like, when liquid water turns to solid ice, what happens? I think is what it says. And that's basically the correct answer, is the molecules move farther apart. I think some of the incorrect answers include the molecules get closer together. That's incorrect. And another incorrect choice would be the surrounding temperature gets colder. A lot of people choose that because you think, oh, it's ice, so things around it are going to get cold. But remember, it's the things around it being cold that turned it into ice. So the ice in this question is not cooling out or cooling off its surrounding environment. The surrounding environment is cooling it off. But anyway, make sure you know this, right? Make sure you know that the water molecules move farther apart as they get cold, right? As the liquid water turns to ice. And this is unique. And I know it's not written here on the slide, and I don't remember if the textbook mentions it or not, but generally speaking, because we've already mentioned what temperature means, right? So generally speaking, when you lower the temperature of something, the molecules are moving less. Therefore, they're getting closer together, right? And also, and you don't need to know this, but very often when we talk about bonds, these covalent bonds between molecules, generally speaking, they have a length. And biology majors, the length. Like you could tell, you would know the length of the covalent bond between the oxygen and the hydrogen of water, depending on the temperature, right? But anyway, the point is, even the molecule itself will compress, because as things get colder, those bonds also get smaller. There's less energy trying to break those molecules, the bonds of the molecule apart. So anyway, yes, that is unique. Most things get smaller at the molecular level when they get cold. Ice, as it goes from liquid water to solid ice, it gets larger. And because of that, the solid ice is less dense than the liquid water that it's in, and that makes it float. So there we go. I wish somebody was online right now so I could ask if you have any questions, but I'm gonna have to move forward because there's nobody to answer or ask any questions. But yeah, so now you know how water floats, right? But let's talk about why that's important. Like, what does that matter? And before we talk about that, this is the picture I wanted to show you earlier. This picture right here, even though we're talking about the biological significance of ice floating, the picture on the right also would have done a sufficient job of demonstrating what I was trying to demonstrate. Or excuse me, the one on the left. This is a better picture for what I was trying to demonstrate when I was talking about temperature, right? And how water moderates temperature. You can see if you look closely, these water molecules look blurry, right? It shows them like moving around a little bit, and it's exactly what it is. So again, imagine I'm going back to what we were talking about earlier with moderating temperature. Excuse me, little tangent here. Those water molecules are moving around a little bit, but they're chained to each other, so to speak. So they can only move around so much. But then eventually, like I said, if there's enough energy, enough heat, they'll move around so much that those bonds will break. But anyway, let's get back off. Let me get off of that tangent and get back to the idea of ice floating. So again, as I mentioned in the slide before this one, this is what water molecules look like when they're liquid on the left, but then when they get frozen, they just assume this shape. And when they assume this shape, you can see it's a hexagon, right? Uniformly, that's the shape it forms. But those molecules are farther apart on the right than the ones on the left, right? And again, because of that, ice floats, right? Ice is less dense than water. So anyway, here we go again. Why is this biologically important? Well, when a body of water gets cold enough for the liquid on top to turn into ice, right? The ice is basically forms a blanket on the top. And that might sound really strange to you, but imagine, I don't know, imagine being in Greenland and imagine I don't know. Actually, I'm not very familiar with their temperature fluctuations, so I'm just throwing a number out there. But imagine you're in Greenland and the ice forms on top of the water and the water drops to, I don't know, let's say negative 15 degrees Fahrenheit, right? That's really cold, really, really cold. But again, it has that has that ice on top. And it's weird because when most people think of blanket, they think of staying warm. But it is indeed the case because it is relatively warm. If you have a body of water and it has a chunk of ice on it, right? That ice, and there's a lot of other things. This is just how you probably have been taught, but so I'm going to keep it this way to keep it simple. But there's a lot of other factors that go into this. But let's just say it's 32 degrees Fahrenheit because that's when water generally freezes. Not necessarily salt water, but that's a whole different discussion. So that's 32 degrees. And again, like I said, which is 0 degrees Celsius, by the way. And let's say, again, the air is 15 degrees Celsius, or excuse me, Fahrenheit, negative 15 degrees Fahrenheit. That's a big difference. So even though it's really cold outside, in the air, the water is going to be protected from that cold air because it has that ice on top. And again, we think of ice as cold, but in this scenario, it's relatively warm. So if it wasn't for that, imagine if ice sank, right? And cold things usually do sink, but ice happens to be less dense than water, so it floats. So imagine things would just get freezing. The water would freeze and it would get cold and sink, right? And then basically the whole body of water would freeze because there's nothing to protect it. Another example, and you can click this link to watch a little video about it. And we have one student this semester who's from Florida, so they might already be familiar with it. This is how I was familiar with it before even learning biology. So when they're expecting a freeze, very often these people who own orange trees, they might cover them with water, right? Knowing that that water will then freeze, which again sounds bad. Like, oh, you don't want to freeze your trees. But then as the air temperature falls below freezing, that ice around the tree is actually going to help insulate it. So yeah, it's cold. That ice is cold, but it's not as cold as the air. So anyway, that is the biological significance of ice floating. And then the last one you're going to learn about is how water is the solvent of life. Right? This is the last property of water that we're going to talk about. Why is water the solvent of life? Before I can teach you that, first of all, you need to know what a solvent is. Before I can teach you what a solvent is, I have to teach you some other terms. And this will be important later, too. Later in the semester, soon, actually, we're going to be talking about something called diffusion and osmosis. And this will be important for that. But anyway, what is a solution? A solution is a liquid with a homogeneous mixture of two or more substances. All right? So think about, I don't know if you know what simple syrup is, but if you take sugar and you boil it in water until it's completely dissolved, once it's dissolved, that means it's a homogeneous mixture. That's a solution, right? Simple syrup is a solution. So to make a solution, we have to have the dissolving agent, the liquid, right? And that is called the solvent. And then we have to have the thing that's getting dissolved, aka the dissolved substance, and that is called the solute. So you need to know the difference between these three terms and their relationship, right? So you dissolve a solute in a solvent, and that gives us a solution. Like I said earlier, when you dissolve sugar, which would be the solute, in water, which would be the solvent, you would get simple syrup, and that would be the solution. Right? You could also dissolve salt, which would be solute, into water, which would be the solvent, which would give you the solution, salt water. So again, those three terms can be very important a little bit for this chapter. But again, later when we talk about osmosis, that will also be important. So make sure you understand those terms. And here's a term I'm probably not going to ask you, but technically, whenever we dissolve something in water, we call that an aqueous solution. So the point being here, obviously, yes, water is a solute, but it's not the only solute, right? We can dissolve stuff in other liquids too, but when it is specifically in water, we do call it an aqueous solution, excuse me. And because of its hydrogen bonds, it can dissolve a variety of solutes and provides a medium for chemical reactions. And salt, and I've already used this as an example, salt water, right? Salt is a great example because water dissolves salt by disrupting those ionic bonds. It's going to make a lot more sense when I show you the picture. Actually, I'll just show you the picture and we'll talk about it. So here we have sodium chloride, right? This is table salt. And we've talked about sodium chloride when we talked about ionic bonds, right? This solid salt, table salt, which is what this picture is right here at the molecular level. This is a solid chunk of table salt. It's sodium chloride, right? It is the reason those molecules are together is because those positive sodium ions are attracted to those negative chloride ions, right? But what can happen is because water has a positive end or a slightly positive end and slightly negative end, they can disrupt those ionic bonds, right? So you can see here, this water has surrounded this positive sodium ion, right? Because remember, the oxygen end of the water is slightly negative, right? So it's just surrounded, right? That part of the water is very much attracted to the sodium. So it's surrounded. That sodium now cannot even get to the chloride. Meanwhile, remember the hydrogen end of water has a slight positive side, right? So that slight positive side is extremely attracted to the negative chloride ion. So again, the water molecules surround that chloride ion. That chloride cannot get to the sodium. So that's how it dissolves. Now you know how. And Again, I guess the next question will be, why is that important for life? Well, your body needs sodium, for example, right? Your body needs sodium. It uses sodium ions. It uses sodium atoms and ions in chemical reactions, and we don't even get into that in this semester. But yeah, your cells use and need sodium for various reasons. But what it doesn't need is sodium chloride. It doesn't do anything with sodium chloride itself. Now, we eat sodium chloride because we need it, because our bodies break it down. Because again, it's not the sodium chloride that our bodies need in this example, it's the sodium. Sort of like if I gave you a big block of Legos and there was like purple Legos and green Legos, and they were just a huge block. And I said, all right, I need you to make me a little purple house. The first thing you would need to do if I asked you to make me a little purple house made out of those Legos is break these Legos apart, right? Because you don't need orange. Excuse me, you don't need the green Legos. You only need the purple ones. So you would have to break that apart so you could use it. And that's exactly what water does with salt, amongst other things, right? It dissolves it so we can get to the stuff that we need. Again, really quickly, another extra credit idea, and you don't have to necessarily wait for me to ask any of these. If you think of anything that sounds like it would be good for extra credit, just go ahead and write about it, right? You'll probably get extra credit. But anyway, like I said, in this example, we're talking about how water dissolves sodium chloride, table salt. What are some other things that water dissolves that your cells need? You could look into that. And also, I think I mentioned it earlier. I said that there are some other solvents. We're talking about water and why it's so important. But what are some other solvents in biology? Anyway, let's move forward. Again, I would normally ask questions, but this is a video, so I can't ask questions. There's nobody here. Here's the last part. I'm glad we're getting to this today. And, well, yeah, hopefully I'll post this in an announcement. That would be very important, very helpful, excuse me, if you were to watch this lecture before you do today's lab. And luckily, today's lab is virtual. So even though I'll be online for it, like I mentioned earlier, you don't have to be. And as usual, the lab itself is not past due until Friday. But anyway, let's talk about acids, bases, and pHs. There's different ways to define an acid, but in our course, this is the definition. It's a compound that releases hydrogen ions. And I don't know if I've ever mentioned a hydrogen ion before. This might be the first time I've mentioned it, but you already know what an ion is, right? It's an atom that has a charge. And we've already talked about hydrogen, right? It has that one proton with that one electron orbiting it. But this is a hydrogen ion, right? It's given up that electron. So it's just a proton, right? A hydrogen ion is just a proton. And again, for this course, that's what we consider an acid. An acid is anything that's releasing these hydrogen ions. Now, there are other definitions, and again, you can look them up for extra credit, but this is what you need to know, right? An acid is something that releases hydrogen ions. So then, what is a base? A base is something that accepts those hydrogen ions, right? So the acid is giving them up, the base accepts it. That's one way to look at it. Another way, and this is the way we're going to look at it, the way we're going to define it in this course, we basically say a base is something that releases hydroxide ions. So again, I wish I could remove all those. Maybe I can. But anyway, you should, for this course, no, I don't have an eraser function. Anyway, for this course, you should associate acid with hydrogen ions, right? Something that gives off hydrogen ions. And a base is something that releases OH ions, which are called hydroxide ions, right? And as you might imagine, you probably could have figured this out on your own if you looked at it long enough. But when you add these H plus ions and these OH minus ions, that's a plus and a negative. Obviously, they're going to be attracted to each other. What are you going to be left with? One oxygen and two hydrogens. So they very often form water. So yeah, again, You definitely need to know for the exam and for the lab, acids release hydrogen ions, bases release hydroxide ions. Um, yeah, which brings us to the pH scale. The pH scale describes the acidity of a solution, right? And another way of saying that, it's the measure of the concentration of H plus ions in a solution. So basically, the more H plus ions it has, the more acidic it is. Now, this can be a little confusing, and I won't talk about the math. It's logarithmic. Um, so rather than get confused with it, just take my word for it. Even though we are measuring the concentration of H plus ions in a solution, 0 is the most acidic and 14 is the most basic, also known as alkaline. So these are things you need to know for the exam, for the lab, right? The lower the number, the more acidic it is. The higher the number, the less acidic it is. Another way I could say that is the lower the number, the less basic it is. The higher number, the more basic it is. And it's important for you to think about that. There's so many ways that I could describe an acidic solution or a basic solution, and you're going to need to know all of them, all the different ways. And to make things even more complicated, every time you move from one to the other in the pH scale, like if you were to go from 13 to 14, for example, that would be a 10 times change in the concentration. Of course, if you're going from 13 to 14, that means it'll be 10 times less H plus ions. But yeah, it's a 10 times change. And I'm going to give you some examples on one of these slides, the upcoming slides. But for now, let me move forward. And this isn't it. Again, I'm going to give you an example in another slide. I just wanted to point out again here, we talk about something being acidic if it has H plus ions, right? We talk about something being basic if it has these hydroxide ions, these OH ions. And you can see in these pictures, right? It's not like this is all H plus ions, but it has more of those than it does the other ones. Therefore, it's acidic. This one on the left, it's not like it's all hydroxide ions, but it is definitely more hydroxide ions than hydrogen ions. Therefore, we call it basic. And of course, neutral, which would be a pH of 7, by the way, that's water. Neutral solution has equal amounts of OH minus ions and H plus ions. But anyway, here's where it needs to get, where I want to give some examples, because this is where it can get a little bit complicated. You're going to have some test questions where I might say something like, when you go from a pH of 10, but yeah, let's say it like this. I might ask about going from a pH of 10 to a pH of 8. And obviously, it's a multiple choice question. So there's going to be a lot of different choices, and you need to choose the correct one. And there's so many ways to describe going from a pH of 10 to a pH of 8. First of all, let me go back to this idea of a 10 times change for every step. And just so I'm not drawing on the same spot, let's look at it like this. Going from 0 to 1, that means that there's 10 times more hydroxide ions. It's 10 times more acidic, right? 10 times fewer, going from 0 to 1 means there's 10 times more H plus ions, right? 10 times more acidic, however you want to say it. But now if you go from 0 to 2, so that's 10, but then it's also times 10 again. So 10 times 10 is 100, right? So if we go from 0 to 2, that's 100 times more acidic. Meanwhile, if we go from 0 to 3, again, we're going to multiply the number by 10. So what's 100 times 10? That's 1,000 times more acidic, right? 1,000 times more H plus ions, 1,000 times fewer OH minus ions. And then finally, one last example, we go all the way from 0 to 4. And of course, I could keep going, but why? I'm not going to waste all your time. Again, multiply it by 10. So what's 1,000 times 10? 10,000. Right? So from going from 0 to 4, oh man, I just realized, I haven't had any coffee. So the numbers match up, but I'm still kind of asleep. So forgive me what I said. If we're going from 0 to 1, it's becoming less acidic, right? 0 to 2, less acidic. 0 to 3, less acidic. 0 to 4, less acidic. So forget it when I kept saying 10 times more acidic, 100 times more acidic, 1,000 times more acidic, 10,000 times more acidic. The numbers were correct, but it's actually becoming less acidic. I apologize for the mistake. But yeah, that's how it works. So again, each step you're going to multiply by 10. So again, really quickly, you might get a test question that says, we're going from a pH of 9, or excuse me, a pH of 10 to a pH of 8. And it's going to ask you to choose which sentence is correctly describes that change, right? So really quickly, if we go from 10 to a 9, we know that's a 10 times change. So 10 to a 9 is 10 times more acidic. And this time I am correct, more acidic, because we are going from 10, a higher number to a lower number. Anyway, so 10 to an 8, we need to multiply that by 100 by 10 again. So 10 times 10 is 100. All right, so we've already figured the math out. It is 100 times difference. Now let's discuss all the different ways we can describe it. So going from a pH of 10 to 8 means things are going to get 100 times more acidic, right? Another way of saying that is things are going to be 100 times less basic. Another way of saying that is there's going to be 100 times more H plus ions, right? And then finally, the last way to describe that is it's going to have 100 times fewer OH minus ions, right? So there's all those different ways to describe the same thing. So for the exam, again, make sure you're good with the math, which means every time you go from one to the next, it's a times 10 change. So be good with the math. And then just think about all the different ways of describing going up and down the pH scale, right? More acidic, less acidic, more basic, less basic, more H plus ions, fewer H plus ions. There's going to be all those different ways to describe it. So anyway, that's it. And I will point out really quickly before we move forward, this pH scale that I'm showing you is just an example. So there's nothing to study. There's not going to be any questions where I say, what is the pH of household bleach? There's nothing you need to memorize. Now, I might, if I'm feeling really generous, give you a picture like this and then ask you that question just to see if you can decipher this simple pH scale. But I will never ask you to memorize any of this. Anyway, speaking of bleach, that is the next word for attendance. And again, I know I just moved by quickly, but you can pause it and rewind it if you need to. But bleach is the next word for attendance. So the screenshot should show that picture of me pointing at bleach. Really quickly, I found this on the internet. I didn't make it, but I love it because this goes back to what I talked about on the last lecture. Is people will try to scare you by chemophobia. They're trying to scare you by using scary words and describing the truth in a scary way. And even though this is just a joke, and I doubt anybody's done this, but it's a good example of how you can use the truth in scary chemical words to scare people. So this says dihydrogen monoxide is an acid with a pH level of 7. Let's break that down first. Dihydrogen monoxide is just another way of saying water, but it sounds scarier, doesn't it? Like if I said, oh my God, I've got to go to the hospital, my kid just ingested some dihydrogen monoxide. That might sound scary, but that just means they had some water. And they say it's an acid with a pH of 7. And remember, like we were just talking about earlier, the idea of acidity and alkalinity, it's all relative, right? So a pH of 8 is acidic when you're comparing it to a pH of 10, even though both of those things are basically considered, basic. So anyway, there we go. We're saying water has a pH level of 7. That's all we're saying, and that's true. It's neutral. And then it goes on to say that's a higher pH than any other acid. And that is true, right? Because anything above that, right? Anything above 7, we consider basic. So if you don't know anything about chemical names like dihydrogen monoxide, you don't know anything about chemistry, like what an acid is, in the pH scale, this could seem scary to you, right? So again, this is just a joke, but it's a great point. It goes back to my idea of people trying to scare you, and sometimes not even necessarily with misinformation, but this time, or sometimes by giving you true statements in a scary way. Anyway, it is now 8:50, so that's it for the lecture. When we come back on Friday, we'll talk about buffers. So remember, send in the email. The email should have a list of all the attendance words. It should have one screenshot for each of those attendance words. It doesn't matter what order those screenshots are in. And again, one question about the material covered in this lecture. And that's it. I'm gonna stop recording. Yeah. See you on Friday, hopefully.